Hi everyone. I mentioned in the last video around 1930 or so we have a very satisfying kind of picture of the world. We've got electrons, protons, and neutrons. Those combine together, create the periodic chart, blah, 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 blah. Through the next couple decades, through atom smashing experiments, people uncovered that there was more to the story. And eventually people settled on this idea of quarks as actually being subcomponents of the protons and neutrons. So now where we sit is we've got the electron. There's no more basic substructure to the electron that's known. And we've got two quarks, the up and the down quark. Now those names don't really have any significance. There is no real upness, there's no downness, to these quarks. It's just a way of indicating that they're two opposite things. And so, don't attach too much to the names of these quarks. They're kind of silly, to be honest. In fact, I'll probably just call it the U and the D quark, just to kind of avoid the nomenclature. But the way the theory works is that these quarks combine together in triplets. And so the proton's composed of two U quarks and a D. The neutron, one U, two Ds. So we've got two U's, two D's in this case. So that's the difference between these is just an up and a down quark. And in order to make the sign, the electrostatic signs work, essentially you have to say that the D quark's got a negative third, the U quark's got a positive 2/3. That's going to be a net 1 here, a net 0 in this case. And so these two quarks combine together in those ways and create the proton and the neutron. And now what we've been calling the strong nuclear force actually is the force that binds the quarks together. So these quarks, the way they lock together in triplets, we're calling, that's actually the strong nuclear force. And what happens is when a proton and a neutron get close to one another, these individual quarks start interacting with one another and actually create the attraction we've been talking about in the binding of the nucleus. So actually this strong nuclear force does double duty. I mean, really fundamentally it's the thing that binds the quarks together. Now, I mentioned that typically the quarks combine in triplets. That's true, but they can also combine in doublets. And the way that works is that each of these quarks has an antiparticle shadow partner, if you will. And in order to get a doublet together, you've got to have a regular particle and an antiparticle that bind together. So the strong nuclear force, the way it works is it binds together triplets of particles, or it binds together particle and antiparticle pairs of different things. So once you kind of lay that theoretical framework down, you can start to explain different ways of combining these kinds of particles together. And actually, what's been discovered is that there are actually 6 of these quarks. There's a U and a D, C, S, T, and B. And they have names. And so these 6 different quarks combining together in triplets or doublets explain that entire particle zoo I was talking about in the last video. And so effectively what we have is we have a second periodic chart, if you will, underneath the nuclei, and that's really what I'm building out here. And we would extend this out to show the 6 quarks. We should slip in the neutrinos here, and there's actually partners for the electron, heavier partners for the electron. There's a muon and a tauon, and those are observed in cosmic radiation, typically, although they're also discovered in atom smashers as well. And so what we have is basically 12 fundamental particles, 6 quarks, 3 neutrinos, 3 electrons. Those are the truly fundamental elementary particles, and we use this quark structure to explain the existence of what are now called mesons and baryons, the protons and neutrons and their partners. Those combine together to create atoms, atoms combine together to create molecules, and that's basically our current explanation of how the world fits together.